The Visual Riddles benchmark is a comprehensive evaluation platform designed to test the capabilities of large vision and language models in interpreting complex visual scenarios, requiring common sense and world knowledge. The benchmark comprises 400 visual riddles, each featuring a unique image created by text-to-image models, question, ground truth answer, textual hint, and attribution. Human evaluation reveals that existing models lag significantly behind human performance, with Gemini Pro 1.5 leading at 40% accuracy, underscoring the potential of Visual Riddles as a valuable resource for enhancing vision and language models' capabilities. The benchmark's main task involves solving riddles in an open-ended visual question-answering (VQA) format, evaluating the ability to detect subtle visual cues and apply common-sense reasoning or world knowledge to formulate answers. Additional tasks include a multiple-choice version of the main task, allowing for easy automatic scoring based on accuracy, and assessing the ability of models to determine the accuracy of open-ended responses in two settings: reference-free and reference-based. Experimental results reveal a significant gap in performance between humans and state-of-the-art vision language models. Surprisingly, the multiple-choice format proved almost as difficult, with performances slightly superior to those in the open-ended task, but with notably high performances when auxiliary data is included. Automated tests show that Gemini Pro 1.5, the top autorater, matches human judgment 87% of the time in reference-based evaluations, proposing a suitable method for evaluating open-ended answers. The Visual Riddles dataset, code, and leaderboard are made publicly available to support future research and model evaluation. The benchmark is hand-curated by 7 designers experienced in generating images with text-to-image models, with each riddle consisting of a synthetic image paired with a question and a corresponding ground truth answer. The study categorizes the instances based on the type of common-sense reasoning and knowledge required, including safety-related knowledge, biological knowledge, cultural knowledge, and more. The research paper presents a comprehensive evaluation of various vision language models on the Visual Riddles benchmark, a challenging open-ended visual question-answering task. The task requires models to solve riddles based solely on accompanying images, and the authors assess the performance of humans and models on this task. Human responses are collected through crowdsourcing on Amazon Mechanical Turk, where annotators provide justifications for their answers and are encouraged to use tools like Google Lens and search engines to research clues. The authors also extract open-ended answers from various vision language models, including large vision and language models and caption generation models. The correctness of human and model answers is assessed using a multiple-choice selection format, where 3 annotators select responses that match the ground truth without any hallucinations. The results show that models face significant challenges in solving the riddles, with the best-performing model, Gemini Pro 1.5, achieving a score of 40%, while human performance reaches 82%. The authors also evaluate the performance of models on a multiple-choice VQA task, where each riddle includes an image and a question with 5 answer choices, and find that this task is comparably challenging to the open-ended visual riddles. The paper further investigates the capability of vision and language models to accurately judge the correctness of open-ended answers to visual riddles through automatic evaluation experiments. The authors then present a comprehensive evaluation of various autorater models in assessing open-ended answers to visual riddles, with Gemini Pro 1.5 achieving the highest performance in both reference-free and reference-based scenarios. The paper also examines models' use of visual cues and generative models' efficacy in replicating images aligned with the riddle prompts, revealing challenges in improving models' visual reasoning capabilities and a unique challenge posed by the Visual Riddles prompts to text-to-image models. The Visual Riddles Challenge is a novel benchmark designed to evaluate the common-sense reasoning capabilities of multimodal models. It involves interpreting complex visual scenarios that require nuanced understanding of visual cues and world knowledge. Recent progress in vision language models has sparked interest in common-sense reasoning, leading to complex visual reasoning challenges within the vision and language domain. Evaluation of factuality has been a focal point in language-only models, particularly for tasks where outputs rely on grounding texts. Metrics such as rouge, blue, and BERT score are used for reference-based evaluations, while reference-free metrics include Summa C, Q2, and FIC. In vision language tasks, metrics like ClipScore, AviBench, and TIFA are used, with benchmarks like MileBench, C-True, Blink, and VibeEval enhancing the rigor of factuality assessments. The Visual Riddles Challenge offers a uniquely stringent test of multimodal model capabilities, requiring both deep world knowledge and nuanced common sense reasoning to interpret complex visual cues. The dataset, although smaller than other benchmarks, was meticulously annotated to ensure a rich and diverse set of common sense challenges. Limitations include the use of generative tools, which might introduce inherent biases, and the possibility that individuals may find certain riddles offensive despite efforts to prevent this. Research papers focusing on high-resolution image synthesis, visual language models, and evaluation metrics for text and image generation are also discussed. Key contributions include improving latent diffusion models for image synthesis, introducing progressive adversarial diffusion distillation, and proposing new benchmarks for evaluating visual and language understanding. The importance of common sense in visual reasoning and the need for robust evaluation metrics that can assess the factual consistency of generated text are explored. The appendix provides essential insights into reproducibility, encompassing detailed explanations and examples regarding model evaluation, analysis, and data collection. The Visual Riddles dataset is accessible on Hugging Face, along with comprehensive information about dataset fields and loading instructions. The authors executed all evaluation code on a single Colab notebook, accessible on their website, utilizing CPU and GPU resources as required. The authors employed a paid plan for models with APIs, enabling them to generate 400 predictions for each task within a timeframe of less than 30 minutes. Table 6 lists the models specified in the APIs and how they were used. The authors extracted textual content from web page URLs using Selenium WebDriver for visual riddles containing attribution fields, resulting in lengthy prompts. The Visual Riddles benchmark was created by 7 experienced designers who generated images using advanced text-to-image models, including Midjourney, Ideogram, Canva, DALL-E 3, and Stable Diffusion. Each image must be sufficiently challenging such that at least one of the evaluation models fails to correctly answer the question based on the provided image. Figure 6 depicts a heat map showing how models and human annotators failed to solve visual riddles in the Visual Riddles dataset, visualizing by the color intensity of each cell. The z-axis represents different categories of riddles, while the y-axis shows the difficulty index levels. Red cells highlight particularly challenging areas, with vertical red bands indicating categories that consistently pose difficulties and horizontal red bands confirming the appropriateness of the difficulty index levels assigned. The research examines the performance of vision and language models on the Visual Riddles Challenge, focusing on the correlations between model failures and human failures across various categories and difficulty levels. The analysis identifies model weaknesses in categories such as object counting, temporal principles, and physical principles, with human performance on physical principles being particularly susceptible to errors. Tables 7 and 8 present the distribution of categories and difficulty levels, respectively. The results show that models and humans struggle more with higher difficulty instances, emphasizing the need for improvement in these areas. The research focuses on the annotation process for visual riddles, emphasizing personalized feedback and the evaluation of human and model answers. Annotators were provided with guidelines and examples, including figures that highlight the need for common sense and world knowledge. The user interface for annotation was designed to facilitate the process, which included a qualification round and personalized feedback. During annotation, each annotator was given the image, question, and correct answer, along with candidate answers from models and humans. The guidelines stressed accurate answers without hallucinations. The cannot determine option was frequently selected by models, indicating hesitation, but providing hints and attributions reduced this hesitation. The performance of various models in excluding cannot determine answers is also discussed, with Gemini Pro 1.5 and GPT-4 showing promising results. The Visual Riddles prompt set highlights the struggle of text-to-image models in generating images that match the given prompts. The discussion also touches on potential negative societal impacts, including biases and potential disadvantages for users with specific cognitive or sensory impairments, and proposes a continuous review process to address these issues. The figures and guidelines presented on pages 21 and 22 of the research paper detail the process of annotating visual riddles for a machine learning task. Figure 9 illustrates an example of the mechanical Turk, M-Turk, user interface page used by annotators to answer questions given an image and a question. This interface is crucial for collecting high-quality training data for visual question answering models. Figure 10 showcases the guidelines provided to M-Turk annotators for evaluating different answers to the visual riddle. The annotator UI page displays the visual riddle, the correct answer, and several candidate answers. Annotators are tasked with identifying which candidate answers correctly solve the visual riddle, providing detailed reasoning for their decisions in the explanation and notes section. These guidelines ensure that annotators understand the criteria for correct and incorrect answers, enabling them to accurately label the data. This labeling process is vital for training and evaluating visual question answering models, as it directly impacts the model's performance and ability to generalize to new, unseen data. The use of M-Turk for data annotation allows for large-scale data collection with minimal cost and time, making it an efficient method for gathering diverse and challenging visual riddles. By leveraging human intelligence through crowdsourcing, researchers can create robust datasets that help advance the state-of-the-art in visual question answering.